So, Thomas, it's a pleasure that you will deliver here for us this seminar, and please go ahead with your seminar.
Yeah, thank you very much, ladies and gentlemen. Thank you very much for having me today. So I would like to introduce you to the Amsterdam modeling suite and show you, based on some example applications, of how quantum chemical results or general computational chemistry can be bridged to applications in the real world. So what do I mean by that? Ultimately, the properties of all materials and thus all devices and all systems are determined at an atomistic level. So it is important to understand such systems, to predict their behavior, and then to use that knowledge in order to improve materials for a given purpose, optimize devices and systems. An example is the solar car here, where basically there are a lot of different components, say solar cells, whose efficiency and lifetime can be improved. There are obviously battery systems for which similar things hold, as well as the capacity and the speed in which they can be charged. And then there are lots of material science questions, for example, the chassis, its mechanical properties, the optical properties of the glass material or the coatings. And then there are, for example, tires whose friction can be studied. Similar things hold also for everyone's favorite toy, the smartphone. There are again a lot of different components, say the big OLED screen, whose individual subpixels can be optimized with regard to lifetime, efficiency, and also the color. Then there's a lot of nanoelectronics where there are lots of potential applications. And then there are battery systems. We will see an example on that in a bit. Likewise, things hold for actual very classical chemical processing, chemical industry, where, for example, in this chemical processing plant, one may have a catalyst and might be interested in its selectivity, in its turnover frequency, or study its behavior with the aim to reduce the poisoning by side product of the catalyst. Also, one might just simply use such knowledge to enhance separation process or general chemical processes, and also with regard to the material of the chemical processing reactor, one might want to study that in order to reduce, for example, corrosion or embrittlement of the reactor material. Things like that are then the focus of a recent project of SCM called ReXPro, where the aim is basically to start from quantum chemical calculations, DFT results on the left side here, and then, for example, to calculate transition states, activation barriers, and reaction rates, to feed then that knowledge over into mesoscale models, say kinetic Monte Carlo, in order to study the population of different species, for example. And then this can be again then transferred over as input or as parameters to a computational fluid dynamics model. And so with that with this kind of endeavors, with such projects, one basically aims at retaining the precision of a quantum chemical calculation, and one tries to transfer it over to a model which is as big as possible, or where a long enough timescale can be studied. And that's also basically what we do at SCM. So we are developing and distributing a series of different programs. These are, on one hand, classical DFT programs here on the lower left corner, BAND and ADF. And then there's a second class. These are semi-empirical codes like MOPAC or DFTB. And then we also have force fields, as well as continuum simulation methods. So all of these programs, they comprise the so-called Amsterdam modeling suite. And we try to combine them in order to exactly tackle this computational chemistry trade-off. So on the one hand, one has very accurate methods available, but they're computationally very expensive. However, one would like to study large models and understand them, optimize them, and also one would like to do the same for processes, which requires often long simulation times. So all of these programs in a recent effort, we tried to merge into the so-called AMS driver. So to have them as a single executable with the intention to share functionality across different programs. This gives them access to a large number of different applications in various different fields for our users. And this is then also accompanied by a graphical user interface as well as a Python scripting environment. So the GUI is the graphical user interface, and Plums is the so-called Python library for automating molecular simulations. To begin with, the first example is about OLED materials and spectroscopy. First and foremost, just some key features of our DFT programs, ADF and BAND. So ADF is a molecular DFT code, BAND is a periodic one. The main take-home message here is that with the use of stable type electron basis functions, we're able to very accurately represent the electron density near the atomic core regions. And together with a proper treatment of relativistic effects, so scalar relativistic and spin-orbit coupling effects, this allows one to accurately describe heavy atoms, so heavy chemical elements. An example where this is of advantage is this study here, where the researchers looked at an osmium dye complex, an OLED material in principle, and they found that it requires actually spin-orbit coupling treatment in order to get qualitatively correct results. You can see this here on the right side. Basically, one needs spin-orbit coupling in order to reproduce this peak in the near-infrared region. Without spin-orbit coupling, one would not get the correct result. So this is first example of where actual heavy elements and their accurate description matters. And that's also the first example of a potential OLED material. However, we were looking here at just the absorption here on the left side. So basically, one excites the system from its electronic ground state into an excited state. However, when it comes to OLED materials, one usually has to deal with different kinds of phenomena. For example, usually one has charges which meet in the OLED layer, and then these charges, so basically electrons and electron holes, and when they meet, they form excited states. They can be either singlet or triplet states, and then there are all kinds of different pathways possible between which the system can then transfer or transform itself. So basically, usually one has an intersystem crossing, which is frequently exploited in OLED materials, which is basically to go from singlet into the triplet state. One can have fluorescent effects and phosphorescent effects. These are the decays upon emission of radiation from the singlet and triplet states, respectively. And ADF provides a lot of different tools to calculate this phenomena, and they usually translate down into different kinds of couplings. So this might be either the coupling between the different states and their vibrational substates. It might be spin-orbit coupling effects, and these are all the things one needs to be able to describe in order to get a proper result. An example, or basically a systematic study of how good is ADF in describing such systems was done in the past by some of my colleagues, and they were performing spin-orbit coupled time-dependent DFT calculations on a series of 23 different OLED dye complexes, and they were assessing the zero field splitting energies and the lifetimes of the triplet states and comparing the results with the experiment. And as you can see here on the bottom on these two graphs, usually the results match up quite well with the experiment. There are individual outliers who can usually be explained in terms of discrepancies between what one has in the computational model and the actual experimental setup and system. However, the accuracy is deemed good enough and is also encouraging in order to, for example, try to move on and systematically tweak OLED materials, for example, to modify ligands in order to alter the ground state or the type of the excitation. This was then done in a somewhat earlier study where the researchers were looking at the iridium complex, and they were modifying its ligands, putting fluorine atoms either here as visible here on the right side, either in para position or in auto position. And turns out that the para position actually affects the radiative rate, so the rate of the radiative decay, emission of radiation, by quite a lot, while the corresponding auto position doesn't matter really at all. It just increases non-radiative decay paths over vibrational levels. And this kind of understanding can then be used, for example, to systematically optimize OLED materials. Also, there's a recent example about so-called third generation OLED materials, which basically try to increase the efficiency of such OLED dyes. The main thing here to keep in mind is that if electrons and electron holes, as said already before, if they meet in the OLED layer and if they are located on a single OLED dye molecule, they basically translate into excited states, and there is 75% chance for this state to be of a triplet multiplicity and only 25% for that state to be a singlet state. And so usually one knows then also from basic physical chemistry that a direct transition between a triplet state and a singlet state is not possible, it's spin forbidden. However, spin-orbit coupling effects, as found in heavy elements, they increase the chance for this process to happen. That's why we saw all these OLED complexes having these heavy elements. However, heavy elements are rather costly, and so for industrial or large-scale applications, one would like to avoid these. And so the so-called third-generation OLED materials, they exploit an effect called thermally activated delayed fluorescence, and that basically means that one is able to convert these triplet states into excited singlet states, from which then in turn a radiative decay can occur. Turns out the dominant rate for this whole process is the so-called reverse intersystem crossing or upconversion intersystem crossing, basically the transformation of a triplet state into a singlet state. And this can be calculated. There's also a tutorial how to do this in ADF. So there matter, again, a lot of different coupling terms matter here, say the spin-orbit coupling. And then one basically uses a modified Marcos model to describe this intersystem crossing rate. And then what also matters, obviously, is a precise description of the energy difference between these two excited states. That's here the red term. And then there are lots of different coupling terms between the vibrational couplings or between vibrational levels of the two excited states involved. And so basically that gives, again, even more confidence. One is able to describe such OLED complexes quite accurately, and the processes, the excited states and everything. However, obviously OLEDs are more than just a single molecule. And what the next thing is, which matters here, is then also the charge transfers. So basically charge mobilities. We already talked about that in this OLED emitting layer, basically there are electrons and electron holes, and they move through this layer. So it obviously matters how fast can they move, are there any losses and things like that. And usually these are organic crystals. So what matters actually is the charge transfer rate between two nearby molecules. And that can be calculated, again, with ADF by using so-called charge transfer integrals. And they do not give only an idea about the mobility of these electrons and electron holes, but also about the anisotropy of this charge mobility. So as you can see here on the lower right, that there are different charge mobilities in different directions, which obviously makes sense. The molecule is not isotropic. There are alternative ways on how to calculate these charge mobilities and deal with this problem of how well do charges move through these layers. an alternative one is basically one uses localized states, for example, by using a constrained DFT formalism, using the electron counts in the different molecular fragments, so the individual molecules, as a boundary condition, and thereby one is able to localize excited states. One can then form between excited states located on two different molecules. One can then form a coupling Hamiltonian, diagonalize that, and get some energy differences as well as mobilities of charges and things like that. And a third alternative way is the so-called frozen density embedding method, where one basically tries to solve the Kohn-Sham equations of A in an embedding potential, which basically originates from the presence of another fragment B. And then there are various different frozen density embedding formalisms. For example, the coupled FDE method, it allows one to obtain response properties in between these two subsystems, and therefore also is then able to deduce such charge mobilities. Again, there are even more ways to do that, to actually simulate electron transport phenomena. Another one would be the implementation of so-called effective mass tensors in bands. So basically, starting from the curvature of the band structure, one is able to derive an effective mass tensor, means one is able to derive electron transport phenomena, charge mobilities in a crystalline material in different directions. And the third method is basically relies on the non-equilibrium Green's function formalism. It is implemented in ADF band and DFTB. And what one there basically does is one puts a molecular device, usually in between two electrical contacts, here on the left and the right side, applies a potential and is, or voltage, and is then able to derive the electrical current, which flows through that molecular device under the influence of this electric field. An example, it moves away slightly from actual OLED materials, but is still an electronic device. This was studied by some of our co-workers or some of our collaborators. And what they were doing, they studied a palladium disulfide slab. That's quite an interesting material because it behaves as a metal if there's more than one layer of this 2D material. And when it occurs as a monolayer, it behaves as a semiconductor. So this has been exploited in this study. Basically, the researchers were looking at how can an electronic diode be realized out of this single material, so out of palladium disulfide, and they found that after certain lengths of this monolayer channel, in that case it was 2.5 nanometers, that system then possesses the characteristics of an electronic diode and basically allows to realize such a system out of a single material. Switching to a totally different topic, what I want to talk about is now actual processes, so things which need to be simulated. I already mentioned the AMS driver before as the common executable of all or most of our programs. And this AMS driver has a lot of different subroutines, driver subroutines for doing various different tasks. There are standard tasks like geometry optimization, the search for transition states, mapping out reaction paths, and things like that. To simulate actual processes, one then usually uses molecular dynamics or Monte Carlo simulations. And often one is confronted with the fact that chemical reactions, they may happen at a longer time scale than one is actually able to simulate. So there might be just rare chemical events, and they may require way too many MD steps or Monte Carlo steps to be actually happen in a simulation. And to overcome that, we have implemented several different methods to accelerate such rare events. An example here is the CVHD, the collective variable driven hyperdynamics. And as this example shows, one is able to simulate the pyrolysis. So basically, when one heats up the material, the chemical decomposition of alkane chains. One is able to simulate that and reach actually timescales of up to the millisecond range. while still staying below 1 million of MD iterations, molecular dynamics iterations. And so one actually is able to simulate such processes, which would otherwise require at least 10 orders of magnitude more steps and be not feasible with current computer setups. Similar things can also be done with the so-called force bias Monte Carlo method. In any case, what one actually needs in order to do that, to make this feasible for reasonably large models, is a decently fast description of the system, a model. And for these purposes, usually reactive-F is used. So this is a reactive force field, which means as opposed to conventional force fields, it is able to describe the formation and dissociation of chemical bonds. And it does so by relying on so-called distance-dependent bond orders, as shown here in this graph. Basically, with increasing distance between two interacting atoms, this bond order changes, and that is actually then used to make this interaction vanish in the limit of long distances. We're recently also working on neural network-based potentials, which are able to do the same thing. In any case, reactive-F is a highly empirical model, so it relies heavily on parameterization. It has a lot of different individual terms, as shown here. And each of these has a lot of different parameters, and they may not always be physical, so they may just be parameters in a model and do not correspond to any physical quantity. This often gives then the problem, basically, when one has a force field which was parameterized on a certain type of system, it may not then be readily transferable to describe a second kind of system. So what one usually has to do then is to parameterize it again or just reparameterize it. And in order to make that a bit easier, we recently added a set of different tools in the Amsterdam modeling suite. For example, ADF train allows one from the graphical user interface to collect and manage training data. And then there are powerful parameter optimizers like CMAAS, which basically allow one to train the model properly and very efficiently, so that one can basically use this then to describe large-scale simulations. And that is also the beginning of the project I want to present here. And this is about batteries, and specifically about lithium-sulfur batteries. So as already said, this project, the researchers started by generating a specific force field for this kind of system. So they used an existing older parameter set and enhanced or improved this then for this kind of battery systems by using additional results from DFT calculations, for example, the interaction at different bond lengths, and also the symmetric breeding mode of the crystal, in order to parameterize a newly specific force field. And this can then be used, for example, to study the cathode side of a battery. In that case, that's a alpha sulfur cathode. And they use then the grand canonical Monte Carlo method, so GCMC, which allows one to keep the chemical potential constant during the simulation, and thereby to add atoms at runtime into the simulation box. And this was then used to simulate the discharge profile of such a lithium-sulfur battery. And as you can see here, starting from the bare sulfur cathode, more and more lithium atoms or ions are added. And then one basically sees two different effects. First and foremost, one is able to simulate the reduction of the battery voltage during the discharge process. So as you can see here, this at least qualitatively agrees with the experiment. And then obviously, if more and more lithium ions are added into the system, the whole system has to expand, and therefore there is a induced stress due to this diffusion of lithium ions. This is one part. However, obviously one would like to simulate the whole battery in itself. So this doesn't mean not only the cathode part, but also in that case a lithium anode part, which is covered by single-walled carbon nanotubes, and then an organic electrolyte material in between them. And so the researchers there used a molecular dynamics simulation in order to study this discharge process. And so yeah, what they actually found was not very surprising, because it's known for these kind of batteries, namely that the electrolyte material, it degrades over time. So basically the lifetime of the battery is reduced. And based on these molecular dynamic simulations, the researchers mapped the kinetic energy or the temperature of the lithium ions. And what they found was that in the beginning of the discharge process, especially on the side of the anode, that the lithium ions are very hot. And they are then able to reach the electrolyte material. And because they have such high energies, they then induce a chemical degradation process, as shown here. They were even able to map out this chemical reaction path, how that exactly happens. However, the main problem is now understood. Basically, the lithium ions they collide with the electrolyte molecules and induce their decomposition. In the second part then, they added a Teflon barrier, a porous Teflon layer on the side of the anode. It doesn't show very well, but if you look closely, there are a lot of green atoms now here on the left side. And these are the fluorine atoms of the Teflon material. So there's a very thin layer on top of these single-walled carbon nanotubes. And this Teflon layer basically serves as a kind of safety net, or basically it reduces the kinetic speed of these lithium ions. And as these temperatures plots then show here again, they are still hot in the beginning, but they stay mostly within the anode material and do not reach into the electrolyte, and therefore, the electrolyte itself, it stays intact, and that greatly enhances the stability of the electrolyte and thus the whole battery system. Similar things can also be studied for other kinds of batteries. There's just a second study showing intercalation of sodium ions in a graphitic cathode material. Again, one is able to simulate these processes. In that case, this was done with a hybrid ground canonical Monte Carlo molecular dynamics driver in a different study with ReXFF. And it also leads, obviously, again, this discharge process, as seen before for the sulfur anode, sulfur cathode. It leads to mechanical changes, or basically changes in the material, and these changes also induce some stress in the material. This can also be studied with the Amsterdam modeling suite. In that case, we also have that on our website. There's a tutorial showing how this is done. In that case, on the example of an epoxide material polymer. And what one basically does is one stretches the unit cell apart very slowly, while allowing still the system to relax and the molecular dynamic simulation to happen. And one monitors the components of the stress tensor. And, you can see here a plot of these. And this allows them to apply principles for materials engineering, basically to gain a linear fit and then define some offset curve. And this in turn then allows one to determine a yield point, basically the point after which the material undergoes an irreversible phase transition, which then afterwards alters its mechanical properties. Similar things were then studied on this sulfur cathode. It turned out that with increasing content of lithium atoms, the material gets more sturdy. That means it's not very surprising, because basically more ionic bonds are formed, and thus these are stronger than just the interaction between sulfur rings. However, after a certain point, obviously the material breaks, and this starts with the formation of little voids in the material, from which then the whole separation and fracture of the material then starts and proceeds. Yeah, besides that, there are even more tools for other kinds of purposes available in the AMS driver. The last I want to mention here is the so-called molecule gun, which allows one to flexibly insert atoms or molecular entities in the simulation box at runtime. And yeah, that becomes handy when one wants, for example, to simulate sputtering processes or chemical vapor depositions and things like that. So yeah, with that, I would like to conclude my presentation. Let me point out our website, www.scm.com, where you can find way more material of what we are actually doing, what has been done with our with our software. There is a lot of documentation, tutorials, and additional material available, and you can also apply for a free 1-month trial version. And if you are a method developer, SCM is generally open for academic collaborations with academic partners. So yeah, feel free to contact us if you think your method would be of interest for us, and if you would like to gain some more exposure by adding it to our software suite. Yeah, with that, I would like to thank you very much for your attention, and I'm very happy to entertain questions.